So we have video issues and things, so I'm mic'd up. Normally, even rooms this size, I don't mic up, but for 7 hours or so, whatever I'm talking today, perhaps the mic's a good idea. So we'll try it that way. We're going to be talking a bit about carbonate aquifers. I'm a guy who was born on top of Silurian dolomite. And I've done carbonate aquifers in various parts of the world. And when I was doing my Ph.D., they said, you know, you're going to need to focus down. My list of talks, you may realize I didn't ever focus down. So we'll try to go through a range of topics. If there's one of them that you've got particular interest in, catch me on one of the early breaks. And if you want to know something in particular and I decide that I didn't throw that slide in there, I'll make sure I include some information about it. So if you've got particular interest on particular topics, let me know before I get to them, and I probably can modify things as we go. The other thing to watch today is I've done an 8-hour lecture before, and so this one's so much shorter. So if you see my degradation rate, it'd be interesting to know what the key parameters are for degradation. Yeah, we'll see how we go. Yeah, Gary said, oh, you know, you want to come down for this, and I've been doing this worldwide tour and going and giving these lectures, and I travel about 30 hours to give a 40 minute to an hour talk. And I'm like, yeah, sure, okay, it's just going down to San Antonio. How hard could that be? And he says, okay, tell me what's between 9 and 4:30. I said, oh, well, noon's good. He says, no, what's between 9 and 4:30? What's the whole thing? Like, oh, okay. So in my life, I have a managed conflict of interest. In the good old days of research, professors are supposed to avoid them, and there's a lot of opinion in academia about whether you should have a conflict of interest or not. The VP for research, when I was a young professor, he said, well, if you don't have a conflict of interest, you're not doing anything interesting. And so managed conflict of interest says you have rules. And so for me, my professor side, I have students, they're locked in a dungeon. I beat them at appropriate intervals to make things come out, much like any other professor. And then commercially, I'm a chief technical officer for a company out of Loveland, Colorado that licenses me from the university, and that's how we do that stuff, and there's rules associated with these things, largely that I'm not supposed to play with money between the two entities, and that I'm not supposed to make students into my corporate slaves. So these are the sort of things you got to deal with, but if you got any questions about that and how I deal with that in life, people ask me all sorts of questions on different sides of that coin. But there's a set of academics that are wholly offended that I do that. There's probably commercial people that are offended that I do that as well. So, but if you got questions about it, let me know as we go.
Before you get going, would you also bring up the fact that you're sponsored by EAA and you're going to do this on your circuit? So for the cameras.
Will do. we got a couple minutes. I can get these things in. So for the morning, we're going to go through, I'm the 2018 McElhaney lecturer. I've got 2 lecturers. You're going to get both of them, one in the morning, one in the afternoon. And so in the morning, we'll play with your mind a little bit and talk about how you think about water. Most of you are probably associated professionally with water, and so I'll still mess around with the way your brain works because you're stuck with your instincts, and your instincts are really hard to undo. So I'll play around with your brain a bit to start. And then the lecture 2, we're going to talk about scale effects in hydraulic conductivity and how to think about a carbonate in ways that allow you to actually match the data instead of trying to force the model to make the aquifer meet what you want the model to say. You're going to actually use the data and treat the aquifer as it wants to be treated. And then we'll talk about the Arbuckle-Simpson aquifer in Oklahoma. And it's useful to talk about that one before we do the next set of things because we'll be talking about a formation that has some issues in Oklahoma. In the afternoon, we'll talk about that formation where it has some earthquakes. And we'll talk about induced seismicity in Oklahoma. It wasn't my plan to become an induced seismicity in Oklahoma person, but I bought a house in 2010 that was on intersecting faults. And I got to experience 6 felt earthquakes a day. So when you start having that, I live with my mother-in-law, and she said, you need to talk about this to the public because I'm tired of my house shaking. And along that way, I developed something I call a scientific referee role, and it's for dealing with science and how scientists who don't particularly like to advocate and don't particularly like to fight could still do a lot of good in environmental problems and moving them forward. So we'll talk a bit about that. And then we'll end with doing some electrical hydrogeology. So if you've been doing physical or chemical hydrogeology, this will be doing it with electrons and figuring out how the subsurface works. And we'll talk about contaminants and water supply and microbes and different things in the subsurface and what those look like from an electrical perspective. So that's the plan. Any one of those breaks or at lunch, if you want to modify what I'm doing, let me know. I'm stunned 120 people want to spend their Friday with me, but I'm very pleased that you came. So, video things going okay? All right. Yep. Melissa's my puppet master today. And a little lower volume. After a year of talks, I know the words to this song. So as we head into the future with water, we've got to think about the fact that we have a problem. And the problem is that we have instincts. And you don't have a lot of instincts about subatomic structure. So if I want to talk about subatomic structure, I could tell you whatever I want. You won't fight me too much. If I want to talk about some technical issue with circuit boards, you weren't born playing with them, so you probably won't fight me. On water, people fight because they know water. They know all about it. They've lived with it all their life. They got instincts about it. And it makes it terrible because if you get data that fights your instincts, you go with your instincts instead of the data. And if you evaluate how to teach and these sorts of things, the hardest thing to teach is something where people's instincts are violated. Because they don't want to accept that new piece of data because their instincts tell them it's wrong. And so dislodging your instincts, if they're incorrect about water, massively difficult. And it's one of our biggest problems in humanity. So I give you a little video because typically my talks have a lot of boredom at the beginning of getting people mumbled around and sitting, and so it gives them something to watch while my talk slide is up there, and it's shiny, fancy things. But it's also supposed to play with your instincts. And you could think about Vegas because relative to moving to the future, it's very hard to think about a more sustainable, well-built environmental city than Vegas. And people have instincts about Vegas. They have an instinct that they might not remember their trip to Vegas. But if you remembered it, you might think about this fountain. People in water might think about what size pumps are there. They might think about flow rates. They might think about evaporation rates. But they might think about sustainability. And whenever we move into the desert, we always throw in some fountains. If you're in a wet area, you don't have fountains in front of the hotel because you're not worried about dying from lack of water. But if you're in Vegas and you're flying in, looking whether you're going to survive, they got to throw some water up in front of the hotel to know that you might make it through the week. So your instincts are your instincts, and I'm going to talk about those, but I'm going to be playing around in your head instead of just having you watch slides. I'm going to go dance around in your head a bit, so we'll talk about that. But this is part of the McElhaney lecture circuit, and Mr. McElhaney was in a conference in Peoria, Illinois, and he decided that we should get kind of organized with groundwater. So they founded NGWA, he was their first president, and now the lecture series is named after him. When I was in Michigan, I met the guy who used to sell him well parts. He was at his 66th Michigan well conference. He'd been going since he was about 19. So he used to sell Mr. McElhaney well parts. So we haven't been doing groundwater for a really long time. People are still around from when we started organizations with this stuff. But this is sponsored by Franklin Electric. And I like to mention that. Some speakers don't mention the sponsor because it's, I don't know, there's money involved or something. I don't mind money being involved in things. And they pay for me to travel around, and they pay for speakers to come around. The other lectureship from NGWA lost its sponsor this year, so they're scrambling around to find funding for that. So I always mention this, so if you see a Franklin Elect person, and you, even if you don't buy a pump, say thanks for sponsoring that so that they'll keep doing such things. It's always nice if somebody will do these things. So in terms of lectures, I categorize lectures as 3 types. You'll probably get all 3 types today. This one is the, you could do summaries and war stories from professors is always that my project went very, very well and that the other researchers in the field aren't as bright as I am, right? That's the basic professor summary, right? We'll do a couple of those. The low price of $9.95 is you got to go to the condo for Boca. I got a good deal for you. It's a good timeshare. You'll love it. This one's a mind alteration. Okay, so I'm going to be playing around in your head. You can gird your loins and prep for that, and you're a good scientist, and I won't get into your head, or maybe a Harry Potter thing where I'm going to invade your brain and make you relive some nightmare from your youth. That's what I'm going to be doing, so get yourself prepared. It does have a cost. I'm a idea credit card of sorts. If I give you an idea, I'm going to be talking some ideas that could make you tens of millions or hundreds of millions of dollars, but I don't have time to do them. So if you take them and make $100 million, I just want 3%. That's all I ask. Now, in terms of mind alteration, one of the first people that did that scientifically was Plutarch. He was the high priest at the Oracle of Delphi. The basic modern interpretation, which has people that fight against it because we don't have great data, is that you had an intersecting fault, you had ethane coming up, and then you'd put a nice girl on a bench, have her breathe ethane, and have her tell you how to run the country. And we've gone back to this method again, but back then, he was writing about such things, and he said, I'm not sure this is a valid scientific method. And they said, you're getting paid by these people. You might want to pipe down. So he also wrote about giving lectures, and he talked about how lectures go and that there'll be people that'll be chatting, there'll be some people sitting in the back of the room, there'll be some people sleeping, a couple sitting in the front, a couple taking notes furiously, and you get the whole range. And I had a student reading about this, and he said, 2,000 years later, our students are exactly the same. And so we're all humans, and we have fairly similar instincts, but he talked about how to play with people's minds and things, and that's the goal of this talk, is to play with your instincts on water. So in terms of that, I'm a professor from a land-grant university. It's really interesting to look in the history of land-grant universities, but they're supposed to be for the non-refined folks of the world to get educated and to get them tools that they need for what they're doing in their days. In the modern land-grant university, if you want to get patted in the head and that you're a good professor in any university, the main thing you should do is not talk to other humans. And that sort of seems like the goal of professors these days. So if I'm going to do good at research, I'm supposed to write grants, and I'm supposed to ask people who study exactly what I study for money to advance that ball. I don't ask anybody else in the world, just people that study exactly what I study. And then if they give me that money, I train people that do exactly what I do, and then we write papers to be read by those people that do exactly what we do. It seems a little bit incestuous and closed off. And I kind of think we should go outside once in a while. So I'm a big fan of actually going to talk to people. And I do the papers in groundwater journals, but I always ended up in Popular Science and the New Yorker because I was talking. By talking, I was asked to be fired by about half the Oklahoma legislature. I was asked to be fired by various people. I was asked to keep my job by various people. It's tricky talking. So there are side effects. But in terms of thinking and talking, I'm going to tell you how my brain works, because I'm going to go mess around in your brain, and your brain doesn't work the same way mine does. So I'll tell you how mine works so that you have a better understanding of what I'm dancing around in there, that you feel better about life. So I'm a lumper, and I categorize people as lumpers or splitters. If you look at a soil column, if you're a lumper, you see soil. If you're a splitter, there's all this detail. You've got these little worm bores, you've got these little sublayers, you've got these different reaction barriers, and you're going to write it all out, and you're going to have this huge amount of detail for that soil column. And I'm going to go, soil. And you go, you can't do that. And so if you're a real splitter, it'll feel bad when I lump stuff together. If you're a lumper, you're like, yeah, I'd put that together. But I'm a mega lumper. I put everything together. Map thinker. I didn't talk till I was 4. I talk a lot since. I was tested for whether my vocal cords didn't work. I was tested for deafness. I was tested for all sorts of things. They actually thought there was seriously things wrong with me. And my mother has now determined that they were right, but it just wasn't with my voice. But if you don't talk, you actually don't do language skills with your brain. You figure out where you're at. And so if you're speech delayed, you're actually better at spatial things. So I can rotate things in 3D in my head. I can do all sorts of weird stuff like that, but my writing sucks. So I really have to struggle to do things linearly because I'm a map thinker and I think in sort of weird patterns and I have to linearize. So if you have slides that I'm going along and you're going, how did he get to there? In my head, it made complete sense. If you're very linear, it might not. And then finally, I'm data focused, which means I'm offensive. I say things based on what the data say, and well, you realize people would be offended by that. I'm like, well, but it's a 4. But a 4 means people should lose their job, or they're going to have this happen to them, or this is going to happen to them, or there's going to be legal consequences. It's still a 4. You know, and so like when it comes to romance, data-focused people aren't that great. My wife has to deal with this. You know, and I give her flowers, and then I tell her I got them on sale. And you're not supposed to do that, I'm told, but it's what the data say. So I'll say things that are offensive to people. I've had somebody get really mad at me at one of these talks because I said stuff, and they're like, but you're talking bad about us. I'm like, no, I'm not. I'm talking about the data. But people perceive that I'm trying to get after them. I'm not. It's just I don't see the emotional side of it. So in your life, you have important people. Here's 2 people for you to deal with. One is your doctor. He's facing you because you probably know your doctor. He takes 1/6 of your economy. He keeps you alive, right? And he keeps you healthy and all these sorts of things that they sell. They wear a nice white coat. They're clean. The other guy, you can't see his face. You probably don't know him. I had a water well that I drank out of as a kid. I have no idea who drilled that. Kept me alive. Did all sorts of things for me, but I have no idea who it was. And he doesn't get 1/6 of the economy. He might like it, but he doesn't get it, and nobody knows who that is. But in terms of humanity, you've got your life and who you think's important. You probably know the guy on the left, but in terms of humans being around, what do the data say about who's important? Right? So what's the data on that? Which is the most important person in data versus your instincts of, I like my doctor. So here's data, and this is from France. And in 1820, one of the greatest ways you could kill off your kids if you didn't like them was to move to the city. You would double the risk of death by waterborne illness. And so if you didn't like your kids, just move to the city. You'll take care of about half of them. This is why cities weren't really big, because it was a fairly risky place to live. So they bring clean water online in 3 different cities in France, and you can see life expectancy jump up. Gives you about 25 years extra life. And if you look at the medical community, when they tell you that they did great things, we cured polio, we have penicillin, we've done all these things, they go back to about 1920. And they see how much we've done for humanity since 1920? Why do you go back to there? Well, that's after all the water guys added most of the life expectancy gains. And people don't ask about, what's it look like back to about 1840? Oh, well, then we didn't really do anything. So the other thing is if we send out a dread flu, that I came down from Oklahoma, I've got the dread flu, and I give it to Gary, and he then gives it to you guys. And we get the hospital system to be greater than 5% needs of dealing with us. And more than 5% of San Antonio wants to show up at the hospital. That medical system will collapse. It's not built for anything more than about 5%. So when you have epidemics and these different things going through, the panic is that you get above 5%. 95% and all your life expectancy gains is due to water. We don't charge enough, but we also don't get enough credit. But you got to really make sure that you understand that. In terms of money, you have droughts, you have floods. Those are huge percentage changes in the GDP. It actually shows up. Now, when it comes to planning, we do flood planning. We try to make it not happen, although we still have floods all the time. And then you have droughts, and the planning for droughts is, we have a drought. It's about the planning mechanism for that. But the great thing about droughts is politicians' boats, and this is in Oklahoma, when their boat is on the bottom like that, they will give you money to study water. So if you need some water research money, and you see his boat sitting like that, go ask him. He will give it to you. If it rains again, he'll take it away. So make sure you get it into a different account. But these are the things you got to keep track of. Now, you as a person will do your water budget. I looked up the medical profession and tried to figure out what do they call it, what do they do for water budgeting, because I figure they're studying humans all the time. They would have the water budget for humans all worked out. Not so much. They have it for babies in prenatal units, because that's a small bag that doesn't feed back very well, and you want to keep it alive, so you got to keep track of the amount of water. So for neonatal babies, they know water budget. For you, not so much, but roughly you're a 42-liter bag of water. Some of us are bigger bags than others. You put about 2 liters a day in, and then about 1.2 comes out as a liquid, and 0.8 comes out as what they call insensible fluid loss. Okay? Comes out as a gas. So almost half of your water budget is gas, and as we sit in this room, we're heating it up, we're putting out CO2, and we're putting out water vapor. You could test this in an airplane. If you ever notice you get tired right before they take off, it's because you've been emitting gases and you've built up CO2 enough that you get sleepy. And they don't ever fix this because having people a little bit of sleepy while they're about to shoot this thing 500 miles per hour forward, it's good if they're a little sleepy in the back. But you'll notice once you take off, you wake up, it's because you're changing CO2 levels. So thinking about your gas phase, you can see effects on you, but you don't think about effects on you, and you don't monitor it very well. You monitor the liquid side. Your highest output rate, 3 liters per hour. Okay, we can take you, stick you in the desert, put you in short sleeves and shorts, and we can dry you out like a nice grape turned into a raisin. And people demonstrate this all the time. They go out in the desert and they die. And you make it so that people can't go out to that part of the desert because they can't quite figure it out because they have this instinct that I've got water, I'm okay. They actually, most times when they die of thirst, they actually die with water on them because they don't understand the output side is gas. They think it's as a liquid. So when you're dealing with that, you're dealing with a really strong instinct. My students on hot days in Oklahoma, they're from someplace in the north or something, they come out, shorts and t-shirt, they're ready to do work in the field. By about 4 in the afternoon, I'm still marching along in my long pants and long sleeves, and they thought I was an idiot the first part of the day because they, you know, it's going to be hot today. I know exactly it's going to be hot today. That's why I'm all covered up. And about 4 o'clock in the afternoon, these nice young people are dropping over, and I'm like, you want to go home now? No, you're old and you're still walking. Well, it's because I understand hydrogeology, folks, and once you learn hydrogeology, you'll come out with long pants and long shirt and keep your water in your body because you can lose it faster than you can put it in. You physically can't replace it at 3 liters per hour. So that's your water budget. And we'll think about your instincts some more. So you don't think about the gas phase, what do you think about that? And whatever you think about that picture is your instincts, right? I'm not going to tell you what you're looking at. You're going to go, okay, well, obviously that's a, and whatever you fill that in with is your instincts. So you might think about it as a glass of water. We have some Europeans today. They might think about it as a glass of American water because Europeans don't put a bunch of ice in their water. I'm, of course, a groundwater person, so I see a nice set of mountains with a porous media basin with good boundary conditions. But that's because I'm a little altered. So when you're looking at that and people see this nice clear rocks and they go and they put their straw in there and they basically install a well and then they consume out of that aquifer, they're fine thinking about that as liquid. But most of it's actually rocks, roughly 60%. Now, Starbucks got sued about this because they were selling iced coffee and somebody was clever enough to realize that mostly they were selling them rocks. And they said, I'm getting ripped off. I'm only getting 40% of what I paid for. And the judge said, well, actually, it's called iced coffee, which is the rocks plus the liquid. You paid for both. Sorry. But if we make that into rocks and we can't see through them, we make it out of quartz or you make it out of some other mineral, and you can't see through them, you can still have 40% porosity, but suddenly that's not a great place to drink from. Suddenly you go, well, yeah, okay, you guys are going to do groundwater. We're sorry that your village doesn't have real water supply because you got to drink out of sand now. I'm so sorry for you guys. San Antonio is one of the biggest cities stuck with groundwater. And for years, them and up in my neck of the woods, Ada, Oklahoma, have been stuck with groundwater, and they've been furiously looking for a place to build a lake because that way they can have a real water supply. But it's based on instinct because drinking out of the ground is, yeah, there's nothing really down there. What are you doing? We're stuck with that. Whereas surface water and things that you can see through, well, that's good water supply. And it's a strong instinct you got to deal with. And your instincts are the things that are independent of reason. So that's from Charlie Darwin. And it's a real problem in terms of dealing with that because you're dealing with that for a whole bunch of people that even the technically trained ones have instincts and they don't realize it. So there's a guy that studies this. Dan's over at Duke, and he studies your instincts and how they affect your reasoning. And mostly he does this for prices and things. He started off in this field because he was burned as a child. And he found that the nurses, when you have a burned victim who's a child, they can actually study data-wise, does this hurt or does this hurt more? And they can ask simple questions, and the child will say, well, this hurts a lot more. Well, that's the way they were changing the bandages, the way that hurt the child the most. And they said, well, the data says not to do that. And the nurses went right back to doing it the way they were doing it with torturing the child. And they said, well, why are you doing that? Well, it feels better to us. We feel like we're not torturing them as much. Well, the data says you are. Yeah, but it doesn't feel right to us. And so if you're tortured enough as a child, you of course become a professor. That's what you do. And as a professor, what he studied was a lot of price setting and a lot of ways irrational worked things to get you to buy stuff. So if we're going to sell you a car and I can price set in your head that $50,000 seems reasonable, if you go and buy the car for $45,000, you got a great deal. If you paid $50,000, you had a fair deal. That's about the right price. And if you paid $55,000, you got ripped off. But if the true price the car dealer wanted was $40,000, well, you always got ripped off, but you felt better about it if the price set was at $50,000, right? And he does this stuff and he looks at whether if I gave it to you for free, would it be better than if I charged you? And a lot of times it's better if I charge you than if I give it away. You'll actually feel differently about it. And so he does all this instinct and data stuff for prices. And so we can think about that for water. So I'm going to sell you a bucket. So I'm going to take one of your rivers, I'm going to put a wall of concrete in there, and I'm going to make a bucket of water for you. So what would you pay? What seems reasonable? And that's the instinctive price set that's set in your head. And you guys are all water people for the most part, so you guys know these things, right? You guys know the price of concrete per volume, and you're going to think about the generation of power maybe, or that, you know, the politician that gave you the money, you could put his boat there and float it instead of being on dirt somewhere. You could think about all these sorts of things and come up with a price. But where's the price come from? It comes from a set price on your instincts. So if I said $100, would it seem reasonable to you? If it doesn't, then your instincts say $100 isn't right. If I said 100 million, would that feel okay? And where it feels okay is where it's price set in your head. So I won't tell you what's in your head. You got your own issues. But if I said 12 billion for a project in Kansas, I was up in Kansas, they wanted to build an aqueduct project for $12 billion. Okay, might seem a little expensive. How about 1.2 billion? Maybe that's okay. Maybe 12 was too expensive. If I said a couple $100,000, well, we're going to redo the state's water, you'd probably go, yeah, I don't know. But what that number is in your head is usually relatively large. 100 million doesn't seem bad to people. Okay, if I'm going to put a wall of concrete in your river, 100 million seems like a reasonable thing for most folks. So here's another bucket. So this is a kilometer deep bucket in Oklahoma, 15% porosity. The pump's flowing at about 1,500 gallons a minute. This is Ada's water supply in Ada, Oklahoma. What's reasonable to pay for that? I'm buying a bucket. I need a volume of water stored for me. If I'm at 12 billion, is that okay? 100,000? The number's typically orders of magnitude smaller in the price set. We did a study in this aquifer for $6 million, and people felt like we wasted all the state's resources. And it's like, well, we have 500 square miles of your state, a kilometer thick, that we need to figure out what the bucket looks like and how it's functioning and how you're going to utilize it. Yeah, $6 million is hugely expensive. How much did that wall of concrete in that lake cost? Well, that cost us $200 million. Okay. Well, that one was worth it. Why? The why really gets them kind of stuck. But the price setting is amazing. So if you look at price setting, this is what it comes out as data. If we look at bottled water industry, if you got a mirror, they explain themselves quite clearly. But you can ask your students, because they tend to bring these little vessels into class with them, and you can ask them, how much is surface water, how much is groundwater? And they'll tell you, well, okay, well, maybe about this much surface and this much in the ground. And they'll come up with some line typically below the label. The data say, well, the cap is the surface water. On a 2-liter bottle, it's about 2 tablespoons. But we don't think about it that way. We think about the groundwater as this little tiny bit at the bottom. Okay? It's a little tiny bit at the top is surface water. Price-wise, this is not an advanced economic study. This is me going and finding surface water projects, looking at their volume and looking at their price, and going, how much did the bucket cost per volume? Costs you about $1 billion per cubic kilometer to build a bucket at the surface. Costs you about 100,000 per cubic kilometer in the subsurface. But if you go to a city that's using subsurface water, minimum about once a decade, and EAA could check me on this, you'll have a proposal that we need to fix our water problems, we need a lake now. We've got to get a lake built. We got to spend about $1 billion per cubic kilometer to get a lake built because we need to be a real city. Why? And it's based on our instincts. So scientists don't have instincts, right? When we draw these nice pictures, this is NASA. We could do this with USGS. We could do this with EPA. We could do this with almost anybody that draws water cycle. And we draw the picture that our instincts tell us about. There's big rocks sitting out there in the environment. They get rained on by clouds. It runs into lakes, big lakes and some rivers. And then there's some lines going up. We teach them about transpiration from plants, evaporation from the surface, and we put groundwater. Okay. Almost all the diagrams look like that. I haven't seen any diagrams that are much different. But if you look at the data, clouds aren't much for storage. Surface water's 2 tablespoons would be at the top of the cap. It'd be this big groundwater diagram, right? And nobody would understand what we're talking about because they don't know the data and their instincts aren't good for that, right? So I do it as boxes. So rain falls out of the sky, a little bit runs off as a liquid, the rest goes off as gas. So in your own body, a little less than half goes off as gas typically. In the environment, it's way much more that goes off as gas typically. And we don't think about that. I talk to the public all the time and they want to take and put in more dams. If we put in more dams, we can catch more water and we'll have more water available. It's like, well, most of your water is actually going up as a gas. You might want to catch that instead. But people don't think about that side of it. Okay, so boxes make it a pretty easy way to say, well, okay, a little bit more goes up as a gas. Okay. And it helps them think about that a little bit, but their instincts are very much against it. So instinct-wise, we teach people to save stuff. We're going to teach you to save gas. We're going to teach you to save water. The chemist really appreciated that I put this in there for them, and I think I got it stoichiometrically correct. But you're going to take some hydrocarbon, you're going to run it through a gauge that tells you how much you put in the car, you're going to pay somebody money for it, and you're going to go burn fuel and use it. And at the end of the day, you don't have a hydrocarbon chain, you got a few gases. Okay, we used fuel. And then they said, well, you should save water. How do we save it? Well, we're going to measure it, you're going to put it through a gauge, you're going to give a guy money. Okay, well, how are we going to use it? You're going to dissociate it into hydrogen and oxygen? No. I'm going to brush my teeth and water my lawn. Oh, okay. Well, what did you do? Well, I either kept it as a liquid or I did a phase change. Right, but we talk about it the same way as if you're burning fuel. But all we're doing is phase changing and adding a little toothpaste foam or getting our grass wet. But we talk about it as a use. But if you want to look at us when we move into an area, and I think about microbes a lot on contaminated sites. So when you think about microbes moving in, you go, okay, what do you guys need and what are you guys going to produce for outputs? I think about humans the same way because now the alien abduction thing is getting kind of bad. So if you looked at us from remotely in space and just watched us move around, when we move into an area, our basic gig is we find carbon to move around, to go eat carbon, and we then generate gas in the form of water vapor. So our entire lives are spent consuming carbon to generate water vapor. And that's, if you looked at us from a distance, that's what we do. You can also check your phone to see where the next place to consume carbon and generate water vapor is. But that's basically what we do for a living, but we don't think about it that way. Language-wise, we do the same thing. Okay, so here's groundwater, and this is groundwater coming out of 60 meters of shale in Australia, a little spring called Warburton that I used to work at. And it's popping out of that shale. There's nothing up at the top. There's no rainfall for the most part. So it's coming out of the Great Artesian Basin sandstones, come up through 60 meters of shale, through a fault intersection and starts to leak, and life forms, and then it evaporates. Okay? So you have a groundwater-dependent ecosystem. Well, who's dependent on it? Well, lots of little isopods and these little plants and these nice little things. We want to protect those. We're going to protect a groundwater-dependent ecosystem. Okay, well, you guys can have some money and you guys can sort out this stuff and protect groundwater. But then if we go to a little bit larger flow, here's a spring in Croatia, and we're flowing at 24,000 liters per second now, and this is coming out, and instead of little bugs and isopods and things like that, we're growing little humans around there. Okay? When we do that, we switch the language, because now this is the shortest river in the world. You can look it up on Google, they'll tell you this is the shortest river in the world. A lot longer than Warburton Spring, and that came up and ran at the surface for a little bit. Well, yeah, but that one's a groundwater system. Why? Well, there's no humans using it. If it's humans, it's surface water. If it's other things, it's groundwater. That's the basic difference. This is really surface water. If you look at data, that's surface water. They appreciate it so much they named it after me, you see. And if we rain about once a decade out there, that thing has water in it, and it falls out of the sky, runs off the surface, and you have a river. But you have a river like it normally is if your river's purely surface water. Well, there's not actually water in there, so it's not really a river. Well, it is from the surface water perspective. It's not from the groundwater perspective. Okay, so if we look at data on these things that we're naming, it's a little different. But our instincts are so strong that if you go out to the Todd River, there is the Todd River Regatta, and they have boat races, and they have water fights, and they drink a lot of 4X beer. But if there's water in the river, they cancel it because you're supposed to pick up the boat and run. But our instincts are that that's how a river works, right? And so we get these nice demos of our instincts coming back at us about how water really works. But the data, basic data of a hydrograph, we can look at surface water pulse coming along, and you can look at a base flow response, and you go, okay, well, there's your surface water response. Otherwise, you just have a sand spit in the middle of Australia. If you have base flow and you have groundwater coming out, well, now you actually have a river. But we keep calling it surface water when it's just a groundwater outcrop. If I call the mining division of any state and say, hey, you guys deal with mines? Yes. Okay, so you guys are the head people for the state for dealing with all our rocks that are worth something? Yes. Okay, can I talk to your outcrop division? They've never given me the outcrop division. I'm like, well, no, just the people that look at the stuff that's at the very top that's scored it out. Now, we don't have one of those. Why would you have that? Like, well, I just called the water board. They have one of those. It's called the surface water division. And they take groundwater and they call it surface water and they made it a separate division. So I was checking if you guys had the same thing for rocks. Well, no, you idiot. And they hang up on me. But functionally, that's what we're doing, right? For the rocks, we don't split it, but for the water, we do, because magically we can see that, so it must be different water. Now, I never understood until I started thinking about this talk as to why airplanes put their website on their wing, until I started taking pictures out the window and I figured out that they think about this stuff. So here's a nice picture outside of Vegas, and over in Vegas, people go, okay, well, turn the fountain off. You guys are wasting water. What do you mean we're wasting it? I like the look of the fountain. Yeah, but you're evaporating all that water. You're spraying it around the desert. Well, but you guys went out to Hoover Dam today, didn't you? Yeah, it was awesome. Okay, well, you guys realize that's evaporating too. Well, how much? Well, about 2/3 of a cubic kilometer per year. That's why it's hazy over Vegas in the middle of the desert, because you've basically built a large evaporation basin to shoot water vapor into the air. Oh, okay, well, that's like the tax on our water storage. That's not that much, right? Well, we can look at how much Vegas uses. Okay, well, what's the valley use? A little bit less than you evaporate. So we'll go into town and scream about a fountain. We won't notice that the, quote, water supply we put outside of town is actually blowing a lot more water into the air than anybody else. And nobody gets upset about the lake. They get upset about the fountain. It's quite interesting. Now, I use this slide at a governor's water conference in Oklahoma. I didn't realize my audience. My assumption today are these are people that work in water in Texas and Turkey. My assumption that day was governor's water conference is people that work on water in Oklahoma. It turns out I was wrong. That audience was there because Oklahoma dams on average turn 50 years old, and our dams were built for a 50-year lifespan. So they had all come in to tell us to build more dams and rebuild dams and rehab dams, and half the audience was people that made money on dams. And I put this slide up. They did not appreciate it. But I asked a simple question: what's the difference between what you call surface water reservoir, surface water storage, and if I wanted to build an evaporation basin? My goal was to get rid of as much water as possible. Would my design be any different than what you call storage? And they're much more expensive than groundwater, so my question is, if Dr. Evil's plan was to make us spend as much of our money as we could to get rid of as much of our water as we could, would his plan be any different than what we call surface water management or water management? And man, does that piss off people that manage surface water. But the data say that's functionally what we're doing. We spend huge amounts of money to evaporate a lot of water, and we call that surface water storage. And so here's one in Texas, and here's a nice one in Colorado. Here's a boat launch in Nebraska. They're really good at doing what they're built to do scientifically by making them a nice flat place with a low moisture gradient and just sit there and shoot water in the air. And if they go dry, the politicians call up and they go, you guys need to put in some wells. Oh, you're thinking about groundwater. Yeah, we need to pump water into that lake. It's gone dry. Okay. Now, if people say, well, it evaporates, but it falls back down as rain, right? Well, we've measured such things. Scientists do these sorts of things. So there's precipitation recycling. Precipitation recycling, if I got a cup of water, it's the odds that if I came up out of that cup as vapor, that I rained back down in the cup. And those odds are 0. If I do the entire planet, though, my odds are pretty close to 100%. If it comes up off the planet, it'll fall back down on the planet. So if we then look at middle-sized areas, you can then compute for that basin what happens. And if we look at the Mississippi River Basin, 100 parts come out of the sky, 22 go off as a liquid, which is way lower than people think. 78 parts go into the sky, 10 come back and fall back down. So if you start cranking up evaporation, it's not falling back on you. And if you think about the entire planet, mostly it's ocean, you're watering the ocean. And that's functionally what we do, and we've got data to support that. So we can also think about pumping. Here's somebody pumping, goes to work at 8 a.m., stops work at 6 p.m., goes to work the next day, pumps some more. Those are trees in Kansas. This is work by Jim Butler up at the Kansas Survey. And Kansas was concerned because they noticed their rivers were going dry. They said, well, you know, there's a bunch of trees next to them. What do you call those things? Phreatophytes? Why do you call them phreatophytes? Well, they use groundwater. They're draining out our rivers. Well, yeah, we can actually watch them pump. They pump all day long. Well, we should kill them all. Okay. And there's been programs for that. We're going to kill all the trees next to the river because we're short of water. And we don't look what's behind the trees right next to the river. We're not really good at that. But if we look behind the trees, and these aren't behind the trees in Kansas because it makes a better picture to do it in Jordan, but we put these little circles of green stuff. Okay? And people call them rainmakers. They call them center pivot irrigation. I call them humidifiers. I call them by what their function is scientifically. They're good at humidifying the air. But people think about the little metal part, and they think about that, and they think about humidity generated by the spraying. And Nebraska had a big program. They're going to get more crop per drop because they're going to think about the nozzles. They're going to think about the sprayers. I think about the green things. And engineers don't always think about plants. I've got an engineer who is working with me, and we'll talk about it later today, but he built this nice thing, and he's monitoring a spring in southern Oklahoma. And when it went above 32 degrees, the data changed. It went below 32, the data changed. He's like, why would the spring care whether it was above or below 32? It's an isothermal spring. It's always the same temperature. I said, the spring doesn't care. The giant trees around it do. He's like, oh, I didn't think about the trees. I'm like, engineers don't think about living things. It's not done. But if we think about the living things, we're worried about whether we have drips out of the metal. We're not thinking about these guys, right? We're not thinking about what they do for a living. And we can think about that, and we got data on that. So if we look at how much you're going to evaporate relative to what kind of crop you are, these guys are good at spraying water in the air. Cotton, corn, sugarcane, really good at spraying it up in the air. If we compare it to pan evaporation here, and this would be a lake pan evaporation, if those little circles in the desert were just water, it'd evaporate this much. Corn gets cranking, and it actually pumps water into the air better than if it was just water in that circle. And people don't think about that. They go, well, it's green. Well, it's a green pump. So you can think about it as a pump. If you want to give it more of a personality, you can think about it as a sweaty plant. And you got the sweaty plants that, you know, they're in their Ph.D. defense and they're just pouring out. And if you want a good Ph.D. defense, you go pineapple in. Those students never go. They're just cool. So this difference is something we don't think about for plants. We think about the pump and the way that the water's going to spray on there. We don't think about the biological pumps. But you're pumping out about 1.5 million liters per growing season with corn. And we don't think about the green part, we think about the metal part. So combine the concepts. We have the mighty Ogallala, and current water supplies are coming from the Ogallala. Irrigation makes this water source uncertain in long-run planning. When we talk about groundwater, and groundwater people do it too, we use bad language. And I don't mean like politicians these days, I mean more like language that's not appropriate for the resource. So we say things uncertain, occult, mysterious, all these words that you go, dating profile, I'm a little concerned. I'm not going with that one, right? Surface water, we say reliable, recreation. We say words that make you feel better about life, right? So we've got this thing, we've got this groundwater, we're stuck with it. What are we going to do? Well, the need for future water is apparent. We should build a dam. What are you going to call it? Well, we're good at words at the surface. We're going to call it Lake Optima. We're going to be optimistic, right? We don't call our aquifer something that make you feel good. We go, the rock's named that, we'll call it after that. We don't give the aquifer a nice name, right? If you go to Paradise Island in the Bahamas, nobody tells you that it used to be called Hog Key, because it's really hard to sell a hotel on Hog Key. Paradise Island's much better. But we don't deal with that for aquifers, but for our lakes, we can name them. This is Lake Optima. And there's Lake Optima. Spent $25 million. There's the boat launch. Really great if you're a civil engineering department. You can look at both sides of the dam. No risk to students getting wet. And that way they can safely look at full dam construction and understand how to do it. But not particularly useful as a water supply in a water-stressed area. And what happened was they had 450 wells pumping. They said, you know, we got a problem, but their problem is their instincts called this surface water, and they called this groundwater, instead of saying groundwater and a groundwater outcrop. So when they started pumping, they got up to 2,500 wells, and they turned it into a losing system, and their surface water became dry because they no longer had an outcrop. But it's because the scientists aren't using language appropriate to what the data say. We're doing language according to our instincts. And I tell people about evaporation basins and groundwater outcrops, and they'll come up to me a few months later and they go, I said it. I said, what'd you say? Well, I called it surface water storage and evaporation basin. Did you feel guilty? Yes. I'm like, that's instincts. They feel bad referring to what the data say. And it's kind of strange, but it works with water very well. So we can look at the modern day Lake Optima. There's the dry creek bed. There's your humidifiers running, making sure we get rid of the water as efficiently as possible. And well, how do we fix this grand problem of that $25 million? Well, you call it the optimal wildlife management area. Now we fixed it. Make sure the language fits your needs. We'll go to the city. Good time to talk to the city. Politicians' boats are on the ground. I put this up, and a politician, actually a lawyer, came up to me afterwards, and he said, that's Lake Hefner, isn't it? I said, yeah, it's Lake Hefner. It's right in the middle of the city. We got nice restaurants around there and things. He says, you put up a number saying it's evaporating. Yeah. Does that lake really evaporate? Turns out it does. Do you have a reference? Lawyer that asked for references. Yeah, I got a reference, this one. Why is it so old? I said, because this was one of the best lakes for evaporating water and quantifying it. The USGS used it as their test case to demonstrate that we can measure lake evaporation. Because you built a lake uphill in the wind with boundary conditions of zero flow. So we just evaporate it all. So it's really good for measuring that. He said, oh. So we got this condition. Oklahoma City actually was founded on groundwater. They started off on wells in a sandstone. And you go, okay, well, we're in a drought. What can we do? Well, you could look at conjunctive use. You could get back to some groundwater use because you got plenty of groundwater. Yeah, but that's occult, mysterious. We haven't used that. That's old-fashioned. We used that when we were desperate at the beginning, but now we have modern water supply. Like, yeah, you got a ton of it. Okay, so we should do a groundwater project. Yep. Okay, what are you going to spend? We'll do $200,000. Okay, well, can we go outside with a drill rig and maybe check some things, maybe look at some things? No, but you can redo the model. It helps to redo the model if you go out and collect data. Yeah, we don't have budget for that. We have real serious budget issues. Okay, surface water guys, what do you want to do? Well, we're in a drought. Yes. Our buckets are empty. Yes. We need to fix this. Okay, what do you want to do? I want to put a pipeline between two of the buckets. What? Well, for about $100 million, I could connect the two buckets, and then we can manage drought. But they're both empty. I know. Well, we're going to fix that with a pipe. And I can't explain that data any better than that. That's why I put the newspaper article to say that they said it and they did it. But that's how we managed water, because that's our instincts, right? Even if they're dry, putting a pipe in there for $100 million is better than spending anything on groundwater. Here's a different way to think about it if you're a disturbed person such as myself. We just take the western side of the city. We built 3 evaporation pans. Okay? We called them reservoirs, but we built 3 evaporation pans. If I took and recharged those 3, and I took that savings in evaporative loss to fund it, I'm going to make 183,000 cubic meters per day of water that the city didn't have because they were spending the time shooting it up into the air. You did what? I was just not going to let you turn it off, put it out as a gas, and you just keep it. Well, how much are you going to charge me for that? Well, my other choice is I could build you a desal plant and maybe take brackish water from this area, and I could desalinate it and give you 183,000 cubic meters a day. That sounds better. Okay, well, we'll compete on price here. So we can go to Tampa Bay. They built a desal plant. 95,000 cubic meters per day, costs about $158 million. So I'm going to make basically double of that by taking away your 3 evaporation basins. I should be able to spend about $300 million. I'll do it for 100. Seems reasonable to me on a price and volume basis. If you try to sell a project for recharge at a $100 million price level, you won't make it very far. Our instincts say you're never going to spend $100 million on a groundwater project. But on a, hey, what's the price of water? What's our way of getting that much around? Much more valid technique at a much lower price. So what typically is going to happen is if I went in with this proposal for a plant like this, they're going to go, okay, well, let's get people to evaluate this proposal. 158 million, that seems reasonable. We've built desal plants around the world. That's their price. Price setting is normal. And we go, groundwater, we got a guy who says he'll do it for $50 million less. What kind of plant's he going to build? He's going to recharge water. Give him $200,000. Right? It's completely instinct and price setting. It has nothing to do about the physics of how much water we're talking about in volume. So if I talked about water management, I would think, okay, it came out of the tap. If you brushed your teeth but kept it in the basin and never changed it from a liquid, that'd be good. If you went out and put it on your lawn and evaporated it, that'd be bad, because now you lost the water. And so management-wise, if we could keep the water around, I consider that good, and I'll put this in units of cubic kilometers. And if we evaporated it all, it'd be bad and be negative loss. So we can look at data from Lenny Konikow from the USGS, and he looked at how are our bottles of water doing around the world. And I put this little tick mark. Some people in this room know people that were born around this time. Nobody is that old, I can imagine, but my parents were born around this time. This is when we invented center pivot irrigation and large-scale dams. We became modern, we got water management, and we became really intelligent. And so we can see how we did with water. There we go, we've fixed water problems, and now we've evaporated about 1,000 cubic kilometers off North America. Lake Hefner is 10 square kilometers. It'd be a 100-kilometer tall column of water we managed to chuck into the ocean. Don't worry, the ocean's only gone up by about 3 millimeters. We didn't drown any kids in the ocean, not due to us. But we evaporated that much. If we look at the rest of the world, we've evaporated about 5,000 cubic kilometers off the continents while fully screaming about the fact we need more water and we've lost water. Well, how are we going to fix it? We need to build more evaporation basins. Why? Because we have a water problem. So why are you building evaporation basins to fix water problems, right? We've gone into Egypt, we're just building, and we're going into Ethiopia. We're just building a new evaporation basin. And they're like, you know, that might evaporate a lot. And I said, well, but this is what you do, right? This is the right thing to do. So we're doing that very well. Now, here's northern India. So on a language basis, they've passed us up in evaporation rate. Are they more advanced than us or less advanced than us now that they have less water around? Did they become more modern or are they less modern? It's tricky on a language basis. Everybody else is evaporating, and the more money you put into water supply management, the more we evaporate. So giving people more money doesn't fix the problem because we basically create lots more ways to evaporate. If you evaporate, it gets salty, and we're stunned by that. But it's the basic side effect. If we have climate change, this gets worse because we have more runoff, and our reservoirs are better at evaporation. So as you go through the future and climate scenarios, all of our constructed techniques are designed to get worse as we go. Dr. Evil was thinking ahead, saying that, well, whatever changed, I want it to get even worse in the future. And that's how we've designed it, and we call it water management. So if I were going to do this and think about sustainable human development, I'd stick the water in the ground. You don't have an evaporation tax. You limit salinization. You spend orders of magnitude less. It seems too cheap. So instead of doing surface water, groundwater needs to charge about 3 orders of magnitude more. And people giggle at that. But I did a groundwater project, and I said, okay, well, we're working on this Arbuckle Basin. What happens the day after we do our report? Well, the day after we do our report, 12 lawyers are going to file suit against the state. Okay, so we need to make this report defendable on a legal basis. No, we can't afford to do that. This is groundwater. Do it on a scientific basis. But we know the next day it'll be on a legal basis. I know, but that would cost money. And people wonder why groundwater systems aren't as reliable and they're more occult and mysterious. And it's like, well, how much did you spend to characterize the two sides of your concrete? Well, we did a full evaluation program and we spent X number of $1 million to evaluate and make sure the foundation is strong. Why'd you do that? Well, we wanted to make sure we were safe. Okay, well, we're going to evaluate this groundwater basin. We have as much as you evaluate the two sides of your dam. No. Why not? One of the problems is the other groundwater reviewers would say, well, they're wasting a lot of money. Groundwater projects don't cost this much. The surface water people would be like, hey, you guys are still way cheaper than us. The other groundwater folks would go, well, that's too much. You can spend $6 million. You're asking for 60. But you should be asking for 60 to 600. The other thing we don't do, we don't have anybody making electric power with groundwater for the most part. There's a couple isolated cases. But if we were dumping water in the ground and making money with it, Instead of people looking down at groundwater 400 feet down going, a lot of power to get that stuff out of the ground, they'd be looking down there going, I have a 400-foot tall dam that I already built. All I got to do is dump water down there and make money. And we've been trying to get one of these built, and people are trying to do it. And so we looked at the math, and I gave a talk a couple years ago talking about this, and a guy came up to me and he said, I thought it was a cute idea. Like, why did you think it was cute? He's like, well, you couldn't really make power with that. Yeah, you can. He's like, I know, I just ran the numbers. You can make megawatts of power dumping water in the ground. I'm like, yeah. He's like, well, you can make serious money with that. I said, yeah, all but the 3% you give me. But we don't think about it this way. We don't think about it as a 400-foot tall dam. When we look at 400 foot to water, we go, we're out of water, let's build another lake. Some other ways to do it. We were in a contest, and they said, we can't forge storm runoff in Tulsa. We need to do something else, and you need to make these rocks work for that. We were the only team with architects that actually dealt with water. We were the only ones that had a soil map, the only ones that had a geology map. And what we did was we built the subdivision such that all the water went in. It actually went in better than if it was a grass field. You're supposed to meet a standard of grass field. We went in better than a grass field, and we had cisterns, we had permeable pavers. We actually plugged energy-wise. We did a geothermal system. We upped the cost about $10,000 a unit, but no water would run off this subdivision. You didn't need stormwater management. And we had to actually come up with a new term, so we called it hydrogeoarchitecture, because the architects don't study water. Hydrogeologists don't know how to build buildings. But if you put them together in a room, they figure out how to do it. And that's what we did. We took students from both and stuck them together. I taught a class in hydrogeoarchitecture last spring. So it's another good way that consultants in hydrogeology can make money is I'm going to convert these subdivisions into an infiltration gallery. Instead of saying, I got to find a place in the city to do an infiltration gallery. Any place you're building a house could be an infiltration gallery. We build these flood control structures. There's about 14,000 in the central US, trying to take the peak off the hydrograph. And then we evaporate it. There's money to build more. I can't get money to recharge one because the budget's not for that. I'm like, well, I just want to take it after you flood it and I want to recharge it. Well, you can build more of these, but there's no budget for recharge. So we've already pre-built settling basins, 14,000 of them across the central US. It wouldn't be much of a budget to turn them into recharge structures. In Oklahoma, we have these little earthquake factories called injection wells. Not all of them are earthquake factories. We'll talk about that in that issue. But what they are is they're going into a carbonate that tends to have very low head levels. You have hundreds of feet of head loss in some case, and you're dumping wastewater in. So build your pump, instead of a pump that runs with power going in, build a pump that runs with water going in and power coming back out. So build yourself a generator. We looked into it for Oklahoma injection wells. They build them slightly too small. We need the top couple hundred feet of casing to be a little bigger. We need about a 10-inch casing. And if you have a 10-inch casing, you can start making money by dumping water in the ground. And then as we develop that technology, oil and gas is really good at developing those technologies to be more portable and more flexible because they want to make money with this stuff. So you've got all these places where we're dumping, we're now down to 1 billion barrels per year going in the ground. That's a good sized river. And if you put power production onto that river, it changed the way you thought about oil and gas. And most oil and gas production areas are short of power because they're trying to deal with really remote areas. It would change some of the power balance of the way that they do production. Modeling. This is a river in western Oklahoma. And this is what I normally do is electrical pictures. So we take an electrical picture, and the mod flow model for this river doesn't work right. So we need to fix the river. So the river is supposed to be this sort of shallow river with brackish water, about 3,000 parts per million, and you can't get a water budget to balance with this simple model of a uniform thickness alluvial aquifer. If you go out and take data, we actually offered to do it for almost free because they wouldn't let us go take data in the field. But we went and took data, and if you did that, you found that the aquifer wasn't uniformly flat. There was this bottom bit. It's actually filled with gravel and fresher water. It's about a 50 cubic kilometer bucket, which on the price of surface water, that'd be about a $50 billion resource of water. My master's student is waiting for his check. But we just went out and collected data because the groundwater model didn't work. Most times we spend time fixing the groundwater model to make it match whatever data we think's happening. But we went from having a couple pixels of data over a kilometer scale to having pixels of data vertically and horizontally. We have thousands of pixels now. And so we can go and look at it and see what's happening. Out in South Australia, we've got this spring. It's where the telegraph station was. And it's fresher than the other springs. And they wanted to know why, and they wanted to know how it's functioning. And you have the Great Artesian Basin coming here and discharging as it smacks into this granite sitting here. And so if we look at that in cross-section, we're going to look at some electrical data up here. We have those sandstones with the shale on the top coming up, and then we have this granite that is smacking into. Well, the granite, turns out it's got a conductor in it. And it comes up here less conductive than the sandstone coming in with brackish water. This is a really fresh little water line coming in. And if you come up to the spring, you get a mixing. Chemically, you can tell you had 2 waters. Geophysically, you can tell you had 3. Okay, so we can look at these groundwater systems, but it involves going outdoors and collecting data and characterizing. And I would say characterization budgets for an aquifer shouldn't be $2 million, $10 million. We did a really big groundwater project. We spent $10 million characterizing. It should be at the $50 to $100 million level, because that's what you're thinking about for surface water. And if you're building a reliable bucket that you want to understand how it's working, it's at the $50 to $100 million level minimum. But we don't think about it that way. When we review projects, we don't do it that way. But we should think about what's the price per volume, what's your evaporative loss, what's the operation and maintenance cost. People love selling desal plants. They don't tell you how much it costs per year to keep one running. And there's a book talking about how we developed water supply in the West. Has very, very little to do with hydrogeology or data. It has to do with instincts and politics. And I tell people, show me a case where groundwater is expensive. And when I ask them to show me a case, I don't mean take an engineering firm who builds dams and then compares groundwater locally against their dam. Because I'll guarantee you every time the dam comes out as the better option. Give me a real fair actual estimate of the groundwater versus surface water. And if you did that, show me a case where groundwater is expensive. It's not possible to do relative to the data that exists out in the environment. So we'll walk you through a foreign example of all these principles put together. And we've got somebody from this country. You may never heard of these countries. They're out, I know the US doesn't think about other countries very much. But there's a river called the Euphrates, a river called the Tigris. They're actually one river or 2 rivers, and there's a fight about whether it's 1 or 2. It might just be the Châtelet waterway that gets called the Tigris and the Euphrates. So there's some issues with what we name things. And what we're going to do is we're going to build the GAP project up in Turkey. And I get asked when I talk about this, are you saying Turkey or Iraq or Syria is doing something wrong? I said, nope. I say they're doing exactly what their instincts tell them to do. Okay, so I'm not blaming anybody in water in this area. What I'm doing is showing you what instincts do. So what we're going to do is we're going to have the philosophy of sustainable human development come out. This is from Wikipedia. This isn't like I pulled this out of the 1930s. This is recent. And we're going to aim to create an environment in which future generations can benefit and develop. You know how well it's going in Turkey, Syria, and Iraq, right? Really stable, lovely environment. And what we're going to do is we're going to build 22 dams and get our evaporation up. Okay? And what we're going to do is have USDA come in and teach them how to raise one of the sweatiest plants in the world. We're going to raise cotton, and we're going to create 4 times as much cotton in that area. Because we're going to get the whole thing evaporating because we're going to be modern, right? We're going to do modern things. We're doing investment in water. So now we've evaporated as much as we possibly can in Turkey. If we go south, we can go through Iraq and look at what the Euphrates used to be. And the Euphrates used to be a freshwater system. Right at the end, it got up around 1,000 parts per million. Now it's basically a brackish water system that gets really bad down to the bottom. And people go, why don't you move back to Al-Naziriyah? Why don't you move back to Fallujah? Because it's not like it used to be even 100 years ago. It's not the same place. It's now a brackish place that they used to do ag in. We can look at the whole basin. So the whole basin wide, the green part is greater than 100 millimeters per year rainfall. The brown part is less than 100 millimeters per year rainfall. It doesn't rain. And there's Iraq, and there's the rivers coming through Iraq. And these little squares tell us pre-development, what was your salinity? So lowest salinity up by where it rains, a little bit higher salinity, and then at the very end of the system, after going through all this dryness, you evaporated enough that you got a little bit brackish. So then we modernized, and we got that. And so we're supposed to go and fix that. Now, anything that went wrong on the south side of the border with Turkey? Well, we built this thing. And back in the 1920s to 40s, we did water planning for Iraq, and we sent in consultants to fix these things and make water better in a place that's run for thousands of years on water on its own. We're going to go in and modernize it. So we built Lake Tatar. That was a gypsum doline. We filled it with water that still had gypsum in it. And we're going to use that to exchange water between the Tigris and the Euphrates, okay? Right outside of Baghdad. If you look it up online, you find two kinds of pictures. You find guys fishing or dead people next to it with battle gear with people. It's not sort of a pleasant sort of thing. I'll show you one of the more pleasant pictures. So this is Saddam's palace. These are anti-aircraft batteries. And there's vegetation, lack of vegetation. So here's the lake. We put water into Lake Tatar. We put it in at 315 parts per million to this day. We put in that fresh water coming down the river. When we first put it in, all that gypsum, we came out at about 1,874 parts per million. Now we just come out as brackish. So we built a brackish water creator. Put their good water in at the top, get brackish out the bottom. You're evaporating about 3 cubic kilometers per year. Baghdad uses 1.3. Look up Baghdad, they're desperately in need of water. Well, you're shooting about 3 cubic kilometers per year right outside of your town, right up into the air as gas. I was supposed to give a talk with my co-author, Dr. Rahi. He works at the University of Mustanshari at Baghdad. I said, well, I should give this talk and do a webinar and have you guys think about these things. He says, you can't give this talk. I said, why? He's like, they're really proud of this lake. They spent a bunch of money on it. Well, that's fine, but it's an evaporation pan that's one of the most effective in the world. So, if you're going to beat our instincts, don't worry about rain or rivers. Think about insensible fluid loss. Where's the evaporation? You can probably name the 3 biggest locations in your basin that run on a gauge, right? The 3 biggest users of water in your basin. You know who goes through the gauge and what those 3 big ones are. You know the big users of water. But can you name the 3 biggest evaporative losses where you're really actually using water? For a lot of basins, it's watering grass, our biggest crop in the US. But most people can't name that. And which agency monitors it? We have a UN Commission on dams. We've got UN commissions worried about water supply on the liquid side. There's no UN commission on evapotranspiration. There's no agency managing evapotranspiration in San Antonio, except as a pure side effect. But it's our major use of water, and we just basically ignore it. And we don't need to eat. We do need to eat, and we will at some point. We don't need to humidify. It's not a part of something we need to do. I was giving this talk, and an Israeli was there, and he says, we're actually doing this. We're creating smaller roots and smaller leaves, and we're playing with this stuff with drip irrigation. We're trying to create plants that, per amount of food they use, they don't transpire as much. So people are trying some of these ideas, but politicians don't know these ideas. They don't think about these issues. But if you think our instincts are any different than anybody else, here's a picture from either Iraq or Kurdistan, and I put up both so I don't offend anybody. But everybody builds hotels with big fountains in the desert. It's the way we do things. That's our instincts. So if you have any questions, I'd be glad to answer them.
The preceding program was brought to you as a community service lecture by the Edwards Aquifer Authority. For more information, visit edwardsaquifer.org.